This video has been supported by PCBWay. Hey guys, Merry Christmas and a Happy New Year from PCBWay and me. I am so lucky to always get the most amazing care packages from them. But this one is extra special. Not only did they send over a set of dainty teacups, with what I have to assume are electroless nickel immersion gold handles, they've also come up with this unique nerdy scarf design. Nobody but another engineer will ever recognize it for what it is. Green solder mask and copper traces obviously. Perfect for the season, perfect for the nerdy wearer. And perfectly on topic for this video, we have what I hope to be the Nanovolt preamplifier to rule them all. For designs like this, PCBWay's organic solderability preservative coating is an absolute lifesaver. Copper saver more like. It keeps it fresh and shiny until it evaporates while reflowing. Or it can just be stripped chemically if you want to use the bare copper surfaces for other purposes. Nowadays, PCBWay offers 0.1mm trace width and spacing in their low-cost standard process. Very useful for hiding some alternative LFCSP package footprints underneath the SOIC parts. Let's call that future-proofing rather than crisis immunity. And I'm not the only one who's getting Christmas presents here today. PCBWay is offering some delicious discounts on their circuit boards and other rapid prototyping services until the end of the year. So go check them out quickly if there's still something on your to-do list. Huge thanks to PCBWay for another year of great sponsorships. Hey guys, it's been over 5 years since we've talked about a Nanovolt meter the last time. It was a Keithley 181 that a young and clueless reps managed to repair through sheer luck back then. With a growing enthusiasm for precision, I ended up using it a lot. And I even sniped the Keithley successor, Model 182, on eBay one day. I didn't get around to film a slightly less clueless video for that occasion. But I can say that these are good Nanovolt meters. Naturally, I wasn't going to be satisfied with good while there is a third generation of digital Nanovolt meters out there. At around 1994, I believe Hewlett-Packard entered the stage, with their first meter in this segment, but pretty much defeating Keithley's second gen in the datasheet specs and features. And then around 1998, Keithley launched their third desktop Nanovolt meter, with comparable specs to the HP box. And this has been pretty much the extent of the Nanovolt meter market for the last 26 years. Except for a few low-volume noteworthy mentions. So what do you do if in 2024 that hunger for the ultimate ultra-low voltage measurement hits you? Keithley, Keysight, or DIY? Our friends at Welectron were the first who agreed to help along this investigation. They've sent over not only one but two freshly calibrated, refurbished 34420As. One OG made in America HP branded unit. And a newer Keysight specimen made in Malaysia. Probably with RoHS compliance and such modern shenanigans. What do you think? Which one is going to be better? We will find out and talk about one of these beauties in absolutely excessive detail in just a moment. But first, a word from our Cal certificate. Welectron's calibration service provider has worked on these literally the day before I filmed this segment. Them being 600 kilometers away from me, and this being 2024, where nothing works reliably anymore, makes this a logistics miracle. Practically, that means that these 7.5-digit voltmeters are still in their 24-hour spec. So for a couple of hours, these are my best 10-volt standards for which I have proof on paper. I may have obtained some much better under-the-counter accuracy. But without a certificate, of course. Those are only issued when big money changes hands. So before all else, I'll measure through my DCV and resistance standards to add two fresh low-uncertainty data points to their history. Calibrierlabor Esenwein have created a pretty good certificate too. They haven't just printed out pass-fail info as many budget options might. They are also describing their methodology, some legal implications, how to read the data, what hardware they used and in what environment. And most importantly, we have the actual test points and what our 34420A thought about those yesterday. Now putting some expanded uncertainty numbers and coverage factors onto my measurements right here is mathematically challenging and not fun. So for now I'll just write down the sum of our inherited Cal Labs uncertainty, plus the meter's 24-hour spec, plus another tiny fraction for a possible ambient temperature deviation. That comes out to about plus minus 8 ppm worst case for the 10 volt DC ranges. And the results align perfectly with all other external traceable comparisons. Wonderful. With a bit of imagination, there could exist a perfectly horizontal straight line through all error bars. So that was an urgent first point of order due to the 24-hour cal spec. But ultimately just a side note. What we are really here for is a few ranges down. 110, 1 microvolt, 110, 1 nanovolt, and 100 picovolt resolution, if you can believe it. Do we believe it, based purely on the display resolution? Consider the following. Here's a $2 pi pico board, gathering and averaging ADC readings over a very long time, thereby gleaning some picovolt data as well. Except it's all wrong. There is unfortunately a good reason why one cannot get infinite resolution out of sensors and ADCs, simply through averaging in software. And it happens to be the very same thing that contenders to the title of nanovoltmeter have to deal with. It's noise, of course, but not just friendly, evenly distributed white noise. If it was purely that, we would get a diminishing but ever-progressing benefit from just simple averaging. Our $2 pi pico nanovoltmeter would be incredibly slow but ultimately viable. Alas, all real-world semiconductors, and mysteriously also biological and celestial mechanics, and the stock market, and almost everything else too, I believe, exhibit flicker noise or 1/f noise below a certain frequency. Here the noise power grows inversely proportionally to the frequency. Or to make that more digestible, larger changes happen, but only rarely. The longer we look, the larger the changes we get to witness. That's why a slow filtering in software only gets us so far. An electronic filter would not be inconceivable exactly. But high-value resistors are off-limits because they are noise sources themselves. And constructing a millihertz RC low-pass with, say, 100 ohm would require a somewhat inconvenient cubic meter of capacitors. So, while there are numerous important specs and features to voltmeters, my nanovoltmeter champion, that is going to become a permanent resident on my desk, will be chosen purely based on this 1/f noise corner. Because that's what ultimately limits its low-voltage performance. Okay. To test this, we short out the meter and record a lot of readings. Many hours or even a day or two. Not just any old short circuit will do, of course. What we need is a high-performance, premium precision short circuit. That may sound like complete audio foolery nonsense, but behold. Both Keysight and Keithley have adopted this LEMO 1S series 4-pin low-voltage connector, but with a special customized contact plating option, none, bare copper. Come on, what else would it be? There's also usually a small pipette with deoxit included with new meters. A gentle contact lubricant to mitigate the adverse effects of copper-copper contacts. Hey, I don't know for a fact that this is the 100% genuine OEM shorting plug accessory, but this tinned soldered wire in here does not strike me like the ultimate picovolt connection. I'd prefer to see something crimped here, but I guess that's not a terminal option that LEMO offers normally. This is fine for nanovolts, because there are never any huge currents or temperature differences. But as a matter of fact, the precision short circuit is not at all an esoteric concept. Even with an ultra-low resistance, thick copper plate, one can detect a small voltage between two terminals, while a current flows through two other terminals. So there's like a whole EEV block forum thread, where people are discussing geometries like tetra junctions, where such effects are minimal. Okay, it totally is esoteric, but it's not nonsense. Fast forward to 100,000 readings later, no signs of exhaustion from the combatants. Let's load their recorded data into an IPython notebook for processing in a library called LPSD and visualization in matplotlib. By using Fourier transformations, it is possible to estimate a frequency spectrum from time series data points like these. Just like those software spectrum analyzers in modern oscilloscopes. We are giving the LPSD function our voltage readings and some time information in the shape of a sample rate. There is a big difference between configured integration time and actual reading output rate, because these meters in the HP family insist on zeroing themselves between every conversion. I'm going to feed the algorithm with the configured sample rate. And there we are, with two big surprises, assuming I haven't made any silly mistakes. First, both meters seem to be mostly equivalent, with the modern Keysight box pulling slightly ahead at the very low frequencies. I was very sure that it would be the other way around. Such low-level differences could just be down to luck and the normal spread of integrated circuit properties. On the other hand, semiconductor fabrication processes have become cleaner, more repeatable and more reliable over the years. And that can lead directly to noise advantages for newer parts. The other semi-surprise is that longer NPLC settings don't seem to have inherent advantages. It doesn't matter if we take the mean of 10 measurements at 10 power line cycle integration times each, or if we straight up asked for a 100 power line cycle reading. But what does all of this gibberish mean in practice? For an equivalent of 5,000 NPLC measurements, really taking 280 seconds including all the overhead, the user manual promises 350 picovolt RMS noise. With the naive code on the right, I couldn't achieve that consistently, but I believe that could be a matter of semantics, like how exactly do they subtract any DC offsets, and then calculate the root mean square value. I did achieve a few hundred picovolt readings of the short circuit plug though, with the advertised 5000 NPLC equivalent parameters, and by using my own periodic zeroing instead of relying on the meter's built-in function. And that is really nice. To answer another question from earlier, when using the built-in filters for this, the least significant hundreds of picovolt digit does begin to carry useful data, not only noise. Of course, to take advantage of this, an experiment needs to be able to hold still for long enough. If we are interested in fleeting, short-lived effects, we are stuck with a few nanovolt noise of single readings. Okay, so as exciting as all of these numbers and statistics may be, right? The Keysight meter is my round one winner, and HP is going back to Wheelectron. After having talked about it for 10 minutes, I think it's time that we actually take a closer look at 34420A and do something with it before the next challenger arrives. It doesn't take a seasoned test equipment historian to see that this guy is closely related to HP's massively popular 34401A 6.5-digit multimeter. Same cued half-width enclosure, same display, same user interface, presumably same ADC and similar digital circuitry. If we must use the front UI to set up anything but the most basic configurations, then there is no way around the menu, which is somehow structured horizontally in a very counterintuitive way. Like we go left and right through submenus and then down into a setting, and then left and right again to change that. That'll take years to get familiar with. But when using scripts, which I do, it's a non-issue really. I like that this one has a built-in current source for standalone 4-wire resistance measurements. In some cases it has even better resistance measurement specifications than a freshly calibrated 3458A. Especially in its lowest 1 ohm range, it has a 100 nano-ohm resolution. But if we combined this with a suitable high current source like a fluke calibrator, we could reliably measure even lower resistances than that. And of course there's onboard math for reading temperature sensors like thermocouples and RTDs like PT100s. Internally, as suspected, this is a 34401A and a high-gain JFET amplifier cat-dogged together. It even has the same custom resistor network as the multimeter. It uses it for the ohms current sources and for the ADC integrator steering. Only the Nanovolt preamp gain setting resistors are outsourced. They are now bulk metal foil or thin film at least, in a hermetic Alpha Electronics Golden Boy dip package. Fancy as that part may be, it is not the protagonist, on whose shoulders this high-performance Nanovolt preamp rests. That would be this guy, a matched JFET pair, normally known as IF3602, just disguised with an HP part number. This is a $70 can of silicon, and I could imagine that to fulfill the meter's target specifications, further selection for the very best parts has to take place before manufacturing. Should I attempt to put into grunts what and how and why? Or are you guys satisfied with the ultra-low noise bullet point in the datasheet headlines? Anybody? Okay, I'll just give it a try. There are not many noise sources in electronic circuits. There is thermal noise, proportional to temperatures and resistances. 1/F or flicker noise, as described earlier. Popcorn or telegraph noise is its own separate thing, but not worth mentioning usually. That's just a sign of a broken part if it occurs. And then there is shot noise, basically a consequence of electrons bumping through the crystal lattice of a conductor and into each other when they flow somewhere. If we build an amplifier with a bipolar junction transistor, we will suffer from a combination of all of these noise sources. Shot noise especially, because we will have the collector-emitter current bumping through the semiconductor and the amplified base-emitter current bumping through the semiconductor. JFETs, junction field effect transistors, are the closest thing to a voltage-controlled resistor. Biasing the GYAT of an N-channel JFET more and more negatively pinches off or raises the resistance of its normally conductive drain source channel. Ideally, there is no current flowing into or out of the gate, so an entire noise source removed. The other effects remain, but are partially negotiable. The Johnson-Nyquist thermal noise of the channel resistance could be improved by cooling the transistor, or by trading in some dynamic range and choosing a higher than normal conductance operating point. The shot noise, no doubt, is already optimized in this high-quality, high-cost part, through large feature sizes and clean semiconductor processes with minimal crystalline irregularities. And that is pretty much all the magic that makes this renowned nanovolt meter work so well, a single fancy part. The surrounding circuitry is a little bit more than this, for overload protection and auto-zeroing, I believe, but really nothing crazy. The auto-zero circuit is, I believe, a DAC that feeds into here to compensate for persistent offsets and help with 1/F noise. And these are the gain-setting resistors in the alpha electronics network. Pleasantly simple, yet evidently effective. So, okay, time to stop beating around the bush. Let's do something with it at last. I've been peddling this pure copper everything propaganda for a while now. But how necessary is it really in practice? These are ordinary quality 4mm banana binding posts. If I had to guess, I would say they are made from nickel-plated brass. These are my favorite pure bare copper ones. They are not super expensive, $5 to $8 or so, depending on how many you need and how quickly. But they are hard to get, only sold in China. And you kind of have to pay a forwarding agent to handle all the bureaucracy. Worth it though, in my opinion. I use them everywhere. And these are the ultimate made-in-America low-thermal binding posts. They used to cost $33.21 per piece. Adjusted for inflation, they are probably more like $40 now, if available at all. And at least $50 after having to import them to Europe. I repeat, $50 for banana jacks. They are appropriately sexy and wouldn't stand out in the BOM of a $70,000 Fluke calibrator. But let's see if they are nanovolt proof. First I'll short out and zero the meter on one side, and then I'll measure the voltage generated across the connection. The thing is, each metal transition is a thermocouple that generates temperature-dependent offset voltages. However, in a closed loop, every such transition has a matching opposing one. Say copper-nickel on the positive lead and nickel back to copper on the negative lead. Assuming thermal equilibrium, these voltages cancel each other out. And so even the nasty nickel-plated brass or whatever reaches a respectable tens of nanovolt reading after a while, unless I touch one side or breathe on it or something. What fancy copper hardware buys us really is much faster settling time after handling, better immunity to air drafts over terminals, and lower offsets due to persistent thermal gradients in instrument enclosures. The gorgeous low thermal parts are, well, especially gorgeous, but also a bit suspicious because of their gold plating. One does not generally deposit gold directly on copper, because those two metals will alloy and look terrible, and it won't even be super immune to oxidation, so the pricey plating will just be wasted. Instead, there's usually a nickel diffusion barrier in between the metals. That may sound like a cardinal sin in the teachings of thermal EMFs, but evidently it's perfectly fine. Let's exercise those ppms a bit more. Resistance standard Fluke Model 742A has just received an external traceable calibration. Not the tightest one ever at plus minus 470 milliohm combined uncertainty, but better than what I had before. What now? Well, I have a few other resistance standards, and to ultimately find out if they are good and trustworthy, I use every opportunity for intercomparisons. The more data points, the more likely it is to find outliers, or otherwise discover greatness in my questionable DIY boxes. A 3458A doesn't have transfer specs for immediately successive resistance readings, only a 2.2 ppm 24-hour accuracy. Not good enough for comparing world-class resistance standards that are drifting 0.1 ppm per year sometimes. If we had a nanovolt meter and a few more well-known resistors, we could do something much more elegant. This is a primitive Hammond voltage divider configured for simply dividing the input in half. If we imitate roughly the same division using our unknown resistor, while measuring voltage between the two centers, we have arrived at a Wheatstone bridge, where conveniently many error sources lose importance. All that matters in this scenario is the reference divider ratio and the exact value of the known resistance. A 1 nanovolt reading over the bridge would indicate a 4 microohm or 2.5 parts per billion deviation. That's how incredibly sensitive this is. Of course, not out in the open, with messy wiring and ESD-safe leakages involved. Due to my regrettable inability to predict the future, I asked Keithley if they wanted to send a champion into the nanovolt meter competition, and boy did they deliver. This is a 30-day loaner model 2182A. Keithley has a much longer history in the low-level measurement field than the HP line, so I have high hopes for this one. It would be tricky to give this one a permanent spot on my desk in the event of it winning, because the Tektronix demo department wants it back, but I'll find a way if it comes to that. This is not a threat to the tech demo department. No idea why it came out like that. Wow, I asked neither party for a calibration, but this one is super fresh as well. Preparation for an evaluation by Marco reps. The precise calibration is essential. Awkward. But yeah, that's another set of traceable readings on my standards. Thank you. Only it won't make a difference in the noise department, which is what I'm after today. Same procedure, same short circuit plug, same algorithm for the Keithley. This one actually exposes much more settings to the user, including full control over the auto-zero cycles. I appreciate that, because in some situations it might be desirable to receive readings at the highest possible rate, and as a 1/f noise countermeasure, 1 auto-zero cycle per second might be sufficient. That's not something that the HP meter offers, and so unfortunately, to keep the comparison fair, Keithley 2 will have to AZ on every sample. Hey, interesting. While the HP manual suggests 100 power line cycles and averaging for the ultimate low noise performance, Keithley says it's optimized for the 1 PLC region. And sure enough, plotting my test results confirms that, especially in the higher frequency band, Keithley loses an entire nanovolt when lowering power line cycles from 5 to 1. Although we have to keep in mind that there is still some ambiguity between configured and actual reading output rate. That might also be a factor here. Not sure why it defaults to 5 power line cycles then. It seems to me like a 1 PLC integration time and digital averaging over 5 samples would be universally better than 5 NPLC integration times. But yeah, now we know. And come to think of it, that must be exactly what HP is doing behind the scenes. See, there are no big differences between settings of 10 and 100. But, and I only just got the idea of testing this at all because of Keithley, this one too seems to benefit from shorter apertures. Let's put everything in the same diagram and see where we stand. My interpretation of this would be that both Keithley 2182A and Keysight 34420A are good. Keithley has the upper hand, or the lower noise, in time-critical applications, such as maybe sensing pulsed power in low-resistance shunts. Keysight has better 1/f noise performance. So in long, averaged measurements, like DCV or resistance comparisons, or when watching thermal RMS converters, it is going to be the better nanovolt meter. Personally, I'm more interested in the latter category, And so, based on my small sample size and subjective preference, I'm going to call this one my round 2 winner. But your mileage may vary. Now we have a bit more time to check out Keithley's other qualities, especially because somebody just made me an irresistible offer and I had to buy my own one. Oops. Oh well. Now at least we have one to tear down. The demo unit was delivered with a very nice low thermal EMF test lead set, including a hint towards them using a special low thermal EMF solder alloy with cadmium for that. And some strawberry flavor lip gloss. You're supposed to dispense microscopic quantities of this with a needle or a fine wire. That way this small ampule should last a lifetime. Model 2182A is obviously related to the 6.5-digit multimeter Model 2000. This one is 6 to 8 times as expensive though, so I feel like they really could have given it the 2-line vacuum fluorescent display that all the higher-end 2000 series devices got. As is, the front-facing interface is about as user-friendly as that of Keysight. Not great, but we'll get along on the few occasions that I don't remote control it with GPIB scripts. At least the menu is vertical as it should be. Keithley does not have built-in current sources for resistance measurements. It's a voltmeter first and foremost, and it's good at its job. That's what matters, but it's a nice touch that the HP, Agilent and Keysight models have that. One big plus in favor of Keithley is that it has an ACAL function, similar to 3458A. So when you've blown all your money on test equipment and can't afford heating the lab anymore, it can eliminate within reason temperature coefficients of the front end and ADC, as well as some of its long-term drift. Here's a Tempco test I made in one summer night, for free with my solar-powered AC unit. All the raw data on GitHub and linked below as always. Another fun observation, and I think a pretty big Keithley advantage. They also make the quirkiest electrometers. No, but that aside, a charge injection, aka the bias current, or the current flowing into or out of the input, due to auto zero and the ADC working. That matters big time, because even if it was just 6 nanoampere, over a 1 ohm cable resistance or source impedance, that would be a 6 nanovolt offset, with nasty AC components that can't be zeroed out. My electrometer here is a long overdue repair project, so we can't trust its digital readout. According to the datasheet, we are looking for picoampere readings. But look what happens if we switch over to 34420A. There's something completely different going on, something large and sinusoidal, like mains transformer parasitics perhaps. Not good. Something like this might not show up in the tests I did with the short circuit plug. Internally, this one is a lot more complex, even though both meters are just JFET front-ends glued to DMM ADCs. No official schematics have been published for this one, and honestly I don't really feel like starting the deep dive myself, so this is all guesswork. The most sensitive parts are hidden away under black plastic covers to keep them thermally undisturbed. This is especially important here, because instead of relying on one very expensive, very tightly selected monolithic JFET pair, Keithley uses discrete plastic-molded 2SK170 N-channel JFETs smooshed together with heat-shrink tubing. There are multiple such pairs here, but they are not connected in parallel as a noise reduction strategy, which would be a good thing to try in a DIY preamp. In this architecture, the extra pairs are more likely for reversing the front end, which is what the FA0 function does once per conversion. The TO220 power parts on the left must be for overload protection, the plastic-molded luxury foil resistors, and the blue axial PTF series on the right determine various preamp gains. The residents of the other, smaller plastic cover seem to be mostly analog switches and a huge film capacitor. Could be constituents of the self-calibration and the optional analog filter functions. The rest is basically a Keithley 2000. Let's do something with it. We are staying on brand for this one. I bought a little goodie on eBay, and miraculously it arrived. With that kind of cushioning. Well, it's a hefty metal box, 70s style, so more like a threat to the other travelers in the postal network. This is a Keithley Model 260 nanovolt source that was sold as broken. Fascinating history on this one. NASA property? Lone pool? Good thing the year 2000 compliance has been established and certified. Good to know that it will not self-destruct due to some calendar overflow. Calibrated at Jet Propulsion Laboratory, Standards Laboratory. And some crystallized cat pee on the side for good measure. It came with this Pomona BNC to tin fork terminal adapter hanging off of its Nanovolt output, so no wonder they thought it was malfunctioning. We know better than that now, don't we? Its output terminals are nicely retracted and protected from air drafts with this door. A European power cord has already been installed, but it seems to have been injured at some point. And it's switched to a strangely specific 234 volt mains voltage. But something tells me that the previous owner has remembered that a bit too late. Internally there's not much to look at. It's simply a Zener-based 11 mA constant current source. To generate constant voltage drops over precision resistor voltage dividers in the compartment on the right. With the 3 light bulbs and light guides going to the front panel, it automatically displays the correct decimal point based on the user's range selection. While these are not terribly high power incandescent lamps, it feels kinda wrong to have such ostentatious heat sources in the last place where we want heat sources. So I think I'm going to swap these for LEDs soon. While the milli and microvolt ranges are pretty mundane, the final nanovolt divider stage is built with special looking, crimped copper-leaded wire-wound resistors. Would it be horrible of me to steal just those? To build a minimalist fixed ratio divider to plug into a fluke calibrator? No worries, not today at least. Because with a new power cord, fuse, some capacitors, and lubrication for the switches, it works quite nicely. As is, we could use it to offset signals ever so slightly, to bring them down into a more sensitive, lower noise voltmeter range, for instance. Here are the Keithley 2182A settings best suited for such a not time-critical measurement. 1 NPLC or the medium reading rate. At least the digital moving average filter should be enabled. I didn't test the optional analog filter thoroughly, but it shouldn't hurt. It's more for 50-60 Hz EMI suppression, I think. We are not in a rush, so we can take the long settling time of a 100 sample filter. When the filter annunciator on the display stops flashing, it is full and settled. Then we can use the rel key to null or delta or tear the meter. Finally, we apply what we want to measure, say 100 nanovolt, and wait for the settling time once more. Yeah, it's 16 or 17% off, I mean. Acceptable for a 50-60-year-old source without any recent adjustments. It's okay, we'll adjust later. Could I interest you in a quick update regarding my Nanovolt rotary switch apparatus from a few videos ago? I got it to work reliably now, but it's still not something I would encourage recreating. The idea was to build a Nanovolt scanner or multiplexer for cheap. But in the end, not so cheap methods were necessary to get it to work well. Here are the problems and some possible solutions. And thank you all for the great comments underneath that video. I've read them all, but I was kinda too far in to start over with something fundamentally different. I wanted to use sensorless stall detection in trinamic stepper drivers for homing, but there was a conflict between the compliance of the wipers and their more or less forceful crashing that is necessary for reliable detection. There are many home sensing possibilities, but in this latest version I just went for the expensive closed-loop stepper motors, with an index impulse output once per revolution. As a response to the wear problem of sliding copper-copper contacts, I wanted to 3D print the wipers and finish them with a cheap piece of copper foil, so that they could be swapped quickly and cheaply by everybody. Such large area parallel faces don't make good contacts, surprisingly. It only takes an oil film or some micro debris to lift the wiper and break contact. The most established contact geometry is some kind of springy multi-finger arrangement. To accomplish that, I've superglued sections of this beryllium copper RF gasket to a slightly higher, less springy wiper version. I used to see weird, very slowly accumulating position errors in the motors. After hours of runtime, the wipers were landing beside their pads. I was so sure that I had some kind of off-by-1 counting mistake in my microcontroller code. I had used micro-stepping without thinking about it. And to keep the whole thing cool, I have to disable all motors while they are not moving. Well, a microstep position is not stable. When a driver is disabled, the motor will snap to the closest full-step position. And that happening many times over without the driver knowing was kind of the problem. I now have a rounding function in place that only parks at full-step positions. My revision 1 consisted of 3D printed blocks per axis, each fitted with a motor, a switch wafer, and a wiper, 6 of those puzzled together with mechanical links, and wired up with countless crimped low thermal EMF bridges. All in all, a very time-consuming assembly. I think it would be best to just bake the 6 wafers and all their default wiring into a single multi-layer FR4 board. Turning all the motor mounts into a single machined acrylic baseplate did not save much time at all. But I was just itching for an opportunity to use my new rigid tapping capability for something real. It may not look as impressive as metal, but believe me, acrylic is much more unforgiving. The slightest Z-axis error will cut and ruin the entire plate, whereas metal fights back and turns small errors into machine deflection. M3 right here, by the way. With those modifications, it's been working continuously for weeks now, without a glitch. By now, the number of switch actuations we've done would be enough for many years, if we only did 1 round of measurements per day. And that is pretty much the video. We've seen that and why JFET-based preamps plugged into a normal voltmeter deliver great performance. But at 1 nanovolt and slightly below, both big brands are approaching their limits. What if there was something other than JFETs, something that isn't as inherently noisy as silicon, but still could give us the first few most vulnerable decibels of gain? Well, there is a legendary company located on a small island on the coast of France. EM Electronics makes nanovolt preamps and whole instruments, based on, or at least incorporating for the first amplification stage, transformers. Not a whole lot is known about the inner workings of their electronic miracles. But we can get an idea of their ideas in a 1983 patent. They are starting out with what looks like a push-pull DC to DC converter. There are unavoidable semiconductors in the first stage still, but these could be modern power MOSFETs used in their low RDS-on saturation region, where they would contribute no more Johnson-Nyquist thermal noise than a 1 ohm resistor. This first stage is a modulator that forms impulses out of the nanovolt input. Those are then amplified slightly by a transformer winding ratio before entering a normal semiconductor amplifier. At this point, copper gain has already put some distance between our signal of interest and the seemingly non-negotiable semiconductor noise floor. Furthermore, since we are handling an AC signal now, we can simply use the DC blocking capacitors to shed any amplifier circuit's offset voltages, unlocking huge gain configurations for us without the risk of clipping. Still, there are countless opportunities for EMI, thermal EMFs, charge injection and pointy harmonics to corrupt our fragile payload. So I'm not surprised that even though the basic principles are out in public, nobody that I'm aware of has managed to show a working replica. Until now. Here's the return of the Raspberry Pi Pico voltmeter. No joke this time, it's already comparable to my competition winner, despite the chaotic construction. But this gets a video of its own once polished and packaged. For now, I hope you found that as interesting as I did. Thank you for your time and see you soon.